Very good morning to all. Yesterday we have completed the numericals which are related to this unit number 3, that is three-phase networks. Today we are going to understand the last topic of unit number 3, which is related to the transformation matrix and the rotating elements and the stationary elements. And this will complete our unit number 3. After that, we will see few of the basic things which are related to the uh, impedance matrix and the admittance matrix. And in this way, we are going to complete our unit number 3. So if you all remember the start of our unit number 3, in the starting itself, we have learned about the impedance form of representation of the three-phase network, as well as the admittance form of the three-phase network. So this we have already seen in the very beginning. Let us quickly take a recap and once again go through the contents that we have seen in the starting of our unit number 3. So let me show here. So we have started the three-phase network, then these were the basics of our unit number 3. Okay, so this one, this equation you have to remember. With the help of this equation, we have to understand our today's topic, which is related to the rotating and the stationary elements. So this is the three-phase network. I hope it's there with you in your copies, because everyone have noted this in your copy when we have gone through the impedance form of the reference of the three-phase network. So quickly we will take a recap of these things and then we will start with our today's topic. Okay, so this is the performance equation. Equation number 1, see from here. This is the performance equation of a three-phase elements in impedance form. So in the left hand side we have VPQA, VPQB, VPQC plus E2B, EPQC is equal to ZPQAA, ZPQBB, ZPQC. Then in the second row we have ZPQBA, ZPQBB, ZPQBC. Then ZPQCA, ZPQCB, ZPQCC. This diagonal elements, I am repeating everything that I am repeating in this class, can be asked in the multiple choice question paper, in the university question paper. So you should all note all these points, whatever we are discussing in the class, right? So ZPQAA, ZPQBB, ZPQCC, these are the self impedances of the element between the nodes P and Q with to phase A, phase B and phase C respectively. That is, if I say what is ZPQAA, so ZPQAA is the self-impedance of the element between the nodes P and Q with reference to the bus, with reference to the phase A. Okay. Similarly, if I say ZPQBB, so it is the self-impedance with reference to the node in between the node PQ with reference to the phase B. Similarly, if we say ZPQCC, so that will be ZPQCC will be the self-impedance of the element in between the nodes P and Q with reference to the phase. Okay, so these are the diagonal terms. So these diagonal terms I have already said what will be the terms. Let us now come to the off diagonal terms. So off diagonal terms are ZPQAB, ZPQ AC, ZPQ, BC. So these are the upper triangular matrix and this is the lower triangular matrix. Lower triangular matrix is ZPQBA, ZPQCA and ZPQCB. So these are the mutual impedances with respect to the phase A and B, phase A and C and phase B and C. Okay, is it clear everyone? Because this is the base from where we are going to start our today's topic. So today we are going to understand the basics of the stationary elements, the rotating elements and the three-phase balanced network element. So these are the 3 points that we will be understanding today. So it is important for us to know what is the meaning of all these points that we are going to understand today. So for these points, what is the basis? The basis is the impedance matrix, the three-phase elements in terms of the impedance form. So this we are going to consider, and with the help of this we are going to start our today's topic. So we will start our today's topic. So today we are going to first deal with the stationary elements. So let us see what these stationary elements are and how these stationary elements will be important for us. So the first topic today is stationary elements. So just now we have seen the impedance form of the network. Similarly, we have also learnt the admittance form of the network, right? So impedance as well as the admittance form of the network is already understood by us. Now, the impedance or the admittance of three-phase stationary network elements. What are the stationary network elements? In the power system network, we have some important elements of the network. What are the important elements of the network? In a power system network, we have, I will write here, power system network. What are the components of the power system network? So power system network components are, so in a power system network, these are the elements which are important. Like without these elements, no power system will be complete, right? So we require transformers, we require alternators, and we require transmission lines, right? So these are the three basic elements of a power system network. So whatever power system network that we will consider, it should have the transformers, alternators, and the transmission line. So with the help of these three elements, we can design a power system network. Now, when we take the case of a transformer, let us take the case of a transformer. We know that transformer is a static device, that is, it does not have any rotating part in it. So that's why we call it as a static device. So the elements like transformers, they are symmetric in nature. Why they are symmetric in nature? Because they do not have the rotating parts in it, and if the elements are balanced, then the diagonal elements of the impedance or the admittance matrix are equal, and the off diagonal elements are also equal. What is the meaning of this? Let me write the ZPQABC. So I will write here ZPQABC. How we had written the ZPQABC in the just now we have seen the impedance form of representation. So you have seen here, this is the impedance form of representation. So I am going to write this matrix as it is. So this matrix as it is, if I want to write, let us see how I will write. So I will start with ZPQ AA, ZPQ AB, ZPQ AC. This is the first row. Then in the second row, ZPQ BA, ZPQ BB, ZPQ BC. Then in the third row, ZPQ CA, ZPQ CB, and ZPQ CC. So this is the impedance matrix. So I will write the impedance matrix here. The same will be applicable for the admittance matrix as well. So what I am writing here is, in the stationary elements, when I consider the stationary elements, the three-phase stationary network elements like, so I will write here three-phase stationary elements like transformers are symmetric. So this is the most important word which I have written here, are symmetric. Okay. Now, if the elements are balanced, so I will write here, if the elements are balanced, then the diagonal, so please note down all this. This may be asked in the multiple choice questionnaire. If there is a question, so there can be a multiple choice question framed based upon this basics. So if the elements are balanced, then the diagonal elements if the elements are balanced, then the diagonal elements of impedance or admittance matrix are equal, and off diagonal elements are also equal. So for which elements we are considering? We are considering this for the stationary elements. So this is important. We are considering this for the stationary element. So this is the point of importance that you have to understand. So in case of a stationary element like transformer, because the three-phase stationary element like transformers are symmetric in nature, and in that case, if the elements are balanced, then the diagonal elements of the impedance or admittance, so this is important, diagonal elements of the impedance or admittance matrix are equal, as well as the off diagonal elements are also equal. So this is what we need to understand. And if we want to write this in the form of equation, how can we write? Let us see. ZPQAA is equal to ZPQBB is equal to ZPQCC. So let's give this a different variable name, ZPQS, because it is stationary. Let us give this as S. Okay. And similarly, if we can write for the off diagonal element. So this is the diagonal element. What is it? Right now, which we have written, it is a diagonal element. Right? So in the matrix, let me show where is the diagonal element. So this is the diagonal element in the matrix. So if we are taking the stationary elements like transformer, in that case, if the elements are balanced, then what will happen? In the bus impedance matrix, ZPQAA will be equal to ZPQBB,
will be equal to ZPQCC. This you have to remember. Similarly, if we take the off-diagonal elements, what are the off-diagonal elements? These are the off-diagonal elements. I am showing it with a different color. You can see here. So these are the off-diagonal elements, the upper triangular matrix and the lower triangular matrix. So these are the off-diagonal elements. So in this case, that is in the case of the stationary elements, in case of the stationary elements, both the diagonal elements will be equal to each other as well as the off-diagonal elements will be equal to each other. What we can write for the off-diagonal elements? Let us write here. So ZPQ AB is equal to ZPQ BC is equal to ZPQ AC is equal to ZPQ BA is equal to ZPQ CB is equal to ZPQ CA, right? So these are all the off diagonal elements, and let us equate these elements like we have written in case of the diagonal elements with a special variable. Let us write this off diagonal also with a special variable. So I will write here M, because the this is the self impedances. The red portion you can see मैट्रिक्स में देखोगे, ये रेड पोर्शन जो दिखाया है ये क्या है? दीज आर द सेल्फ इम्पिडेंसेस. सेल्फ इम्पिडेंसेस है, इसीलिए मैंने इनको एक स्पेशल नाम दिया. क्या नाम दिया मैंने इनको स्पेशल? सो चेक इट आउट व्हाट नेम आई हैव गिवन. द नेम दैट आई हैव गिवन इज ZPQS. तो ये S यहाँ पर इंपॉर्टेंट है. S का मीनिंग है सेल्फ इम्पिडेंस. ओके. सिमिलरली यहाँ पर मैंने क्या नाम दिया है इनको? ऑफ डायगोनल के सारे एलिमेंट्स को, इनको मैंने नाम दिया है ZPQM. व्हाट इज द मीनिंग ऑफ M हियर? द मीनिंग ऑफ M हियर इज म्यूचुअल इम्पिडेंसेस. ओके. सो व्हाट आर ऑल दिस एलिमेंट्स? दीज आर द ऑफ डायगोनल एलिमेंट्स. क्या है ये सारे एलिमेंट्स? ये सारे एलिमेंट्स जो है ये ऑफ डायगोनल एलिमेंट्स है. सो इन केस ऑफ ए स्टेशनरी एलिमेंट, है ना, जो अब हम किसकी बात कर रहे हैं? हम स्टेशनरी एलिमेंट्स की बात कर रहे हैं. इन केस ऑफ अ स्टेशनरी एलिमेंट क्या हो रहा है? स्टेशनरी एलिमेंट्स हमारे पावर सिस्टम में कौन से एलिमेंट्स होते हैं? हमारे पास जो ट्रांसफॉर्मर्स होते हैं हमारे सिस्टम में कनेक्टेड, एक कोई भी पावर सिस्टम नेटवर्क अगर हम लेते हैं तो दीज आर द 3 बेसिक एलिमेंट्स जिसके बगैर पावर सिस्टम नेटवर्क कभी भी फॉर्म नहीं हो पाएगा, राइट? सो इफ वी वांट टू डिजाइन any power system network, we require these 3 elements. These are the 3 basic elements. उसमें से ये जो ट्रांसफॉर्मर है, this is a static device, right? And as this is a static device, the elements concerning with this device will be symmetric in nature. ठीक है? So 3-phase stationary elements are like transformers are symmetric, and if the elements are balanced, then the diagonal elements of impedance or admittance matrix are equal. So this we have to remember. The diagonal elements of the matrix impedance or admittance, जैसे मैंने यहाँ impedance लिखा वैसे ही हम admittance के लिए भी लिख सकते हैं. So in both the cases, that is in case of the impedance as well as in case of the admittance, the diagonal elements will be equal to each other as well as the off diagonal elements will be also equal to each other. है ना? कैसे लिखेंगे हम ये? इस तरीके से हम लिखेंगे दोनों इक्वेशंस के फॉर्म में, द फर्स्ट वन एंड द सेकेंड वन. दिस सेट इज corresponding to the diagonal element and the diagonal elements are given a special name ZPQS, where S stands for the self impedances. Okay. Similarly, these are all the off diagonal elements which are constituting the mutual impedances. तो क्योंकि म्यूचुअल इम्पिडेंसेस है इसलिए हमने इनको नाम दिया M. सो जैसे हमने ऊपर लिखा कि इन केस ऑफ द एलिमेंट्स आर बैलेंस देन द डायगोनल एलिमेंट्स आर इक्वल, तो इसीलिए हमने लिखा ZPQAA is equal to ZPQBB is equal to ZPQCC and this is equal to ZPQS. ठीक है? S is for the self impedance. Similarly, जब हमने बोला कि ऑफ डायगोनल एलिमेंट्स भी इक्वल है एक दूसरे से, तो ऑफ डायगोनल एलिमेंट्स कौन कौन से है? ऑफ डायगोनल एलिमेंट्स आर ZPQAB, ZPQBC, ZPQAC, देन इनके रिवर्स, तो ZPQBA, ZPQCB और ZPQCA. So these are the off diagonal elements. So off diagonal elements को हमने स्पेशल नाम दिया है ZPQM. So this we have to remember. These are the off diagonal elements and these are the diagonal elements. So जैसे हमने अभी diagonal impedance के लिए लिखा, so similarly we can write for the admittance also. तो अगर मैं admittance के लिए लिखूं तो कैसे लिखेंगे हम? for admittance, एडमिटेंस के लिए कैसे लिखेंगे? एडमिटेंस के लिए लिखेंगे इस तरीके से, YPQAA is equal to YPQBB is equal to YPQCC, and let us give this name as YPQS. So this will correspond to the diagonal elements, and similarly if we want to write for the off diagonal elements, it will be in this way, ZPQAB is equal, YPQAB is equal to YPQBC is equal to YPQAC is equal to YPQBA is equal to YPQCB is equal to YPQCA, and this is equal to YPQM. So this belongs to the off diagonal elements. So these values will correspond to these elements will correspond to the admittance matrix. So in terms of admittance matrix, what we can write is in this way. So this is for the admittance matrix. So these are the diagonal elements and these are the off diagonal elements. Okay, is it clear everyone? Where we can write here, where I will write here, what are these components? Let us write here. ZPQS is self-impedance. ZPQS is self-impedance across PQ of each phase, right? So ZPQS is the self-impedance of across PQ of each phase. Similarly, ZPQM will be mutual impedance across mutual impedance of phases, right? So mutual impedance of phases across PQ. Okay. Similarly, for YPQS, what we can write is, it is the self admittance and similarly YPQM is the mutual admittance. So in this way we have defined the stationary elements. Okay, so this is what we understand by the stationary elements. Now let us consider the rotating elements. So as we have just now seen that in any power system network we will have transformer, alternators and the transmission line. So transformers are the static device. Similarly, there are some devices like alternators which are the rotating devices. So in case of the rotating devices, there will be rotating elements available with us. Let us see what is the case with the rotating elements. Now, in this case, the impedance or the admittance for a balanced three-phase rotating elements like alternators. Okay, so I will write here like alternators. So like alternators, motors. So there are even motors available with us, which will be forming the load part of our system, etc. Right? Uh, Now the impedances and admittances here are not symmetric. So this point you have to remember. The what we can write here is at impedance impedance and admittances are not symmetric. Why it is not symmetric? Because you know that these devices are continuously rotating in nature. They are not static devices, right? So as they are not static devices, so their impedances and admittances are not symmetric. What is the reason? Reason is that because they are constantly rotating. They are constantly rotating. Okay. So as they are constantly rotating, their impedances and the admittances will not be symmetric, and the what we can write for this is that important. This is an important statement. Please make it a star mark. What we can write for this is that, in other words, the mutual impedance, of phase A, the mutual impedance of phase A with respect to B is not equal to the impedance of B with respect to A. Is that clear, everyone? So like in the previous uh, element, that is the stationary element, what we have written is ZPQAB is equal to ZPQBA. I will just show it once again so that you all understand it. So you can see here, this is admittance form. I will go back to the impedance form. So here you can see that ZPQAB is equal to ZPQBA, right? So ZPQAB means the mutual impedance of phase A with respect to B, and ZPQBA means the mutual impedance of B with respect to A. So in case of a stationary element, what is happening is the mutual impedance of between the elements with respect to A and B is equal to with respect to B and A, right? So this is what we can conclude from the stationary element. But this is not the case with the rotating element. Why? What is happening in case of the mutual impedance of a rotating element? So in case of a mutual impedance of the rotating element, the mutual impedance of phase A with respect to B is not equal to the impedance of the B with respect to A. Okay, so if I want to write in the mathematical form, how I can write, let us see. So I can write here in this way: ZPQAB will not be equal to ZPQBA. Is that clear, everyone? Please reply on the chat box. Is that clear, everyone? What will be happening in case of a rotating element? In case of a rotating element, the mutual impedance of the phase A with respect to B will not be equal to the mutual impedance of phase B with respect to phase A. So this is what we can understand with the help of the mathematical equation. So if it is not equal, then how we can write the things? Let us say How the things can be written, let us write here. So we can write the equation here in this way. So let us write here ZPQAB will be equal to ZPQBC will be equal to ZPQCA. This is the first pattern. So let me give this name as ZPQM1, that is mutual impedance 1. Similarly, if I replace the sequence here will be BA, here it will be CB, and here it will be AC, right? So this will be equal to another sequence. Let's give this name as M2. Okay, so these are the off diagonal elements. So off diagonal elements will be having the terms in this way, and the diagonal terms will be equal to each other here. So I will write here ZPQ AA will be equal to ZPQ BB will be equal to ZPQ CC, that is equal to ZPQ S. So this will be same as it was in the case of symmetric also, but in case of the off diagonal elements there will be change. So here in case of the rotating element, there is a change in the off diagonal element. So there will be two concepts here. One is ZPQM1 and the second one is ZPQM2. So ZPQM1 is related to the what we can say the upper triangular matrix, and ZPQM2 is related to the lower triangular matrix. Okay, so is it clear till here, everyone? This is the last portion of our unit number 3. So this we are going to complete it today. So this is our rotating elements. Is it clear, everyone? Shall we move to the next topic? Have you all written till here? All these things are very important. They can be asked in the multiple choice question paper. All these things which I have underlined here, please make it a note in your copies. This may be asked in the multiple choice question of the university question paper. Okay. Okay, so let's then move on to the next topic related to this. The next topic is three-phase balanced network element. So let me write here three-phase balanced network element. So when the excitation is balanced, you all know what is the meaning of a balanced excitation. So balanced excitation means the three-phase system which is perfectly balanced in all the conditions. That is, all the phases are separated with each other by a phase angle of 120 degree each. So the excitation of any three-phase system is balanced when the source voltages or currents of all the phases are equal in magnitude and displaced each other by an angle of 120 degree. So how we can write the performance equation? Let me write here. So the performance equation, I will write here the performance equation of a balanced, the performance equation of a balanced three-phase network is, let me write the equation. So if we can write the equation, we can write it in this way: EPQ ABC is equal to EPQA, EPQB, EPQC. And now we will be taking the help of our alpha operator, which we have already studied in EPS2, right? So in case of EPA, it will be right. So EPQ B angle 120 degree. So denoted by here, you will note this, and in case of C, it will be at an angle 120 degree. So we will denote it by alpha. And here we can write it in this way, EPQ A, if we are taking A as the reference phasor. So A is taken as reference, and you all know what is alpha. Alpha is equal to 1 at an angle 120 degree. So what will be alpha square? Alpha square will be equal to 1 at an angle minus 120 degree. So this we have already studied in EPS2. So this will be the case if we take the impedance form. So this equation is corresponding to the impedance form. Similarly, if I can write in the admittance form, what we can write here is JPQ ABC is equal to JPQA, JPQB and JPQC. Again, this will be equal to 1 alpha square alpha multiplied by JPQA. Again, I have taken A as reference. Okay, so this is what we can understand from these two performance equations. And if we will substitute this alpha operator in the performance equation of the impedance form, let us write this in the impedance form. So if we use this balanced excitation system, so let me write here the phase voltages and currents, the phase voltages and currents are balanced, right? The phase voltages and currents are balanced if excitation is balanced, right? So if excitation is balanced, then the three phase voltages and currents are also balanced. Now the equation in impedance form, let us recollect the equation in impedance form. So we have written this. So this is our equation number 1. We have already written this. So what I will do is I will make use of the alpha operator, and I will what I am going to do is I am going to multiply this 1 alpha square alpha, which is the balanced excitation, to both sides. Let us see what will happen if I will multiply this equation number 1 with 1 alpha square alpha to both the sides. So let me write here, multiply equation 1. So I will write here, multiply equation 1 with 1 alpha square alpha. So if I multiply equation 1 with 1 alpha square alpha, what will happen? What is going to happen? Let us see here. So this is my equation 1. So I will have to multiply 1 alpha square alpha to both the sides. So this will become 1 alpha square alpha multiplied by VPQA, VPQB, VPQC, right? And I have taken A as reference. So I will replace this complete term with VPQA, this complete term with EPQA, and this complete term with IPQA. So this I am going to do here. So let us see how this equation will get modified. So let me write the equation. So the equation will be here in this way, 1 alpha square alpha. Then this will be multiplied by, as I have taken VPQA as reference. So this will become VPQA plus 1 alpha square alpha 1 alpha square alpha multiplied by EPQA. This will be equal to, now in place of the diagonal term I will replace with ZPQS, and in place of the off diagonal terms we will replace by M. Now as we are considering here the what we are considering here a balanced system. So in case of a balanced system, what is happening is off diagonal terms are also equal to each other. So what I can write here, let me write here. So this will be ZPQS. Instead of AA, I have written S. Instead of this AB, I will write M. Then again, instead of AC also, I will write M. Right? Because this is a balanced system. Then ZPQ, again M. Then here ZPQS, because self impedances are equal, which is represented by ZPQS. So this will be in this way. Then again I will write ZPQM, ZPQM, and diagonal term again ZPQS. Okay, so this is what I can replace, and then I will multiply by 1 alpha square alpha multiplied by IPQA. As A I have taken as reference, so I will add A. Okay, so this is what we can write this equation, and let's give this equation as two equations were already used in impedance and admittance form. So this will be equation number 5. Equation number 5, multiply equation 5 with, I will use the matrix in this way: 1 alpha alpha square. Let us see what happens. So if I will multiply this matrix with 1 alpha alpha square, what will happen? 1 alpha alpha square multiplied by this complete matrix. What will be this complete matrix if you will multiply? So you will get here the result as 1 plus alpha cube plus alpha cube. This will be the result which you will get if you will multiply 1 alpha square alpha with 1 alpha alpha square, right? Because you will get in this way: 1 multiplied by 1 means 1, plus alpha square multiplied by alpha is alpha cube, plus alpha multiplied by alpha square, that is alpha cube. So this you will get in this way. Then I will write here VPQA as it is, plus again this equation, this matrix multiplied by 1 alpha alpha square, you will get again this type of matrix: 1 plus alpha cube plus alpha cube multiplied by EPQA. This will be equal to, so if you will multiply here with this complete sequence, and when you will solve this complete matrix, what you will get here is, I am writing the simplified form: 3 multiplied by ZPQS minus ZPQM. I have written the simplified format. When you will multiply this alpha with this alpha 1 alpha square alpha multiplied by 1 alpha alpha square, again you will get 1 plus alpha cube plus alpha cube. This you will get alpha cube and alpha cube is equal to 1. Alpha cube value is equal to 1. So 1 plus 1 plus 1, that will be 3. Right? So 3 multiplied by this complete term multiplied by this IPQ, sorry, not X, IPQA. So again, if you will solve this, the value of alpha cube is 1. So 1 plus 1 plus 1, this will be 3 VPQA plus 3 EPQA PQA is equal to 3 ZPQS minus ZPQM multiplied by IPQA. So from here what we can get 3 as a common term, and if we will take out this 3 as a common term, the what equation that we will get, let us write here, we will get the equation in this way. Let me write the equation. So we will get the simplified equation in this way. VPQ A plus EPQA is equal to ZPQS minus ZPQM multiplied by IPQA. So this is the simplified equation if we take the balanced three-phase excitation system. So our equation will be in this way, where what we can write here, where ZPQS minus ZPQM, this is the positive sequence impedance, which can be denoted by ZPQ1. So I will again write here ZPQS minus ZPQM is equal to ZPQ1. So this is most important. This can be asked many times in the multiple choice questionnaires. So this you have to remember. This is in case of the balanced excitation system. Is it clear, everyone? This is in case of a balanced excitation system. So as I have already said that in unit 3 mostly the theory comes, and unit 5, which is in or with unit 3, numerical comes. So in case of numerical, we have to derive the Z bus 0, 1, 2 first, and then write the necessary calculations, and then we have to solve the various fault current equations which are asked in the unit number 5. But in unit number 3 mostly theory is expected. So in theory all this type of questions can be asked in the multiple choice question paper. Is that clear, everyone? So this you have to remember. This is the equation which is to be remembered in case of the balanced excitation system. The value of the positive sequence impedance is ZPQS minus ZPQM, where P and Q are the nodes between which the element is connected. Okay, you all know what is it. So if 1 and 2 is the node, if there is a 2-point bus in this way, 1 and 2, and if between 1 and 2 you want to calculate, so this becomes Z12. So Z12 and 1, this one will represent positive sequence impedance. Okay, so this is what we understand by this nomenclature, that is ZPQ1 means P and Q means the node in between which the element is connected. Okay, so we will stop